Now that we've seen how the Schrödinger equation may be used to solve the energy of a particle moving freely along a line, let us now consider what happens if we restrict the movement of the particle to only a portion of that line. This problem is usually referred to as the particle in a one-dimensional box and is a common application of a quantum mechanical model to a simplified system consisting of a particle moving horizontally within an infinitely deep well from which it cannot escape. The solution to the problem gives possible values of E and the wave function that the particle can possess, of which when squared gives us the probability of locating the particle at a certain position within the box at any given energy level. To solve the problem for a one-dimensional particle in a box, we must follow our big recipe for quantum mechanics. First, we need to define the system as well as set the boundary conditions. Next is to solve it using the Schrödinger's equation. And lastly is to define the wave function and allowable energies so that we could arrive at a solution to the particle in a box. Let us consider a particle of mass m that is confined to a one-dimensional box of length L. The potential energy is 0 inside the box, represented by V equals 0, and goes to infinity at the walls of the box. We assume that the walls have infinite potential energy to ensure that the particle has zero probability of being at the walls or outside the box. The time-dependent Schrödinger equation for free particle is represented by this equation, equation number 1. So this equation can be modified for a particle of mass m free to move parallel to the x-axis with zero potential energy everywhere, resulting in a quantum mechanical description of free motion in one dimension as can be seen in this equation number 2. We can take this to yield a general equation shown in equation number 3 where a, b, and k are constants. By applying the boundary conditions we have earlier to the general equation, we can now solve for the constants and plug them back in. So by doing so, we define the wave functions represented by equation number 6. By solving k in equation number 3, we found out that the solution to the particle in a box is given by this equation, equation number 7. So as can be seen here, energy as a function of quantum level turns out to have only discrete integer values given by this, wherein n is equals to 1, 2, 3, etc., and no other values. So the value of the particle is said to be quantized and the energy n is called the quantum number. Note that the quantization arises naturally from the boundary conditions that we've set earlier, and the energy is inversely proportional to that of the mass and length of the box. Several important conclusions can be drawn from this model. As we've said before, the kinetic energy of the particle is quantized. Second, the lowest possible energy of the particle is not actually zero, but is equal to the left-hand side of this equation. This is called the zero-point energy and means that the particle can never be at rest because it will always have kinetic energy. This is also consistent with that of the Heisenberg uncertainty principle, because if we have a particle that has a zero energy, we would know where it is in both space and time, but we all know that is not the case. Also, the square of the wave function gives us the probability density. In fact, this density wave function looks just like a standing wave that is set up in a vibrating string but have positive values. Also, the energy of the system is inversely proportional to that of the mass and the length of the box, and the quantum mechanical solution shows that there cannot be a uniform probability density for the molecule. Here we have a particle in box wave function plot that was done in desmos under some various conditions. So plotted in here are different things. So here we have the wave function plot that is represented by this half sine wave in blue. We also have the probability density represented by this violet, and as well as the energy as a function of n in this green line. Okay. On the sides, you also have these small green lines. So you can see here, these are the energy of the orbitals. For example, n equals 1, n equals 2, n equals 3, and so on and so forth. So if we vary the parameters, say let's start with n. So if you've got a n equals 1, we have a half sign for the wave function and one hump as well for the probability density. If we increase n equals 2, now we have here a full sine wave for the wave function and two humps for the probability density. If we increase n to 3, we have here for the wave function positive, negative, positive, and 3 humps for the probability density plot. Okay, the same trend is also prevalent if you increase the n. Okay, for L is in the denominator, so there is a inverse proportionality with the individual energy states of the of the box, and as the L increases, the energy states becomes compact, but as you decrease the L or the length of the box, the energy increases. Okay. For M, it has no effect to the wave function, but it does an effect on the energy. So as the mass of the object gets smaller, quantum behavior becomes more apparent and the energy differences becomes more separated. As the mass becomes bigger, energy levels gets closer and the quantum effect goes away. So that's the basics for the particle in a box wave function. One application of 1D particle in a box is on UV basis spectroscopy. Let us consider the molecule butadiene. So this molecule has a delocalized electron in this conjugated system. By using the BIB model, we can make predictions on energy transitions that can occur in this molecule. To be able to do this, the first thing that we need to know is what's the length of the box. In this case, what's the length of butadiene? We can calculate that by using its bond lengths, and it turns out to be 578 picometers. Second, we need to know the number of electrons that goes into this. Butadiene has 4 pi electrons, which occupies the 2 lowest energy pi orbitals when in ground state. In terms of n, we would expect that a electronic transition from 2 to 3 would occur. If we can calculate the energy difference between the two, we can compare that to the actual value of photons that will be absorbed by butadiene. The energy difference equation is equal to the energy of n equals 3 minus the energy of n equals 2 using the equation that we previously derived. And since we already know the mass of the electron, and by using some relations that we already know, such as the speed of light and Planck's constant, we can rearrange the equation to solve for the wavelength. And if we plug the values and solve for it, we end up with 220 nanometers as the wavelength needed to make the transition from the second to third energy level. And this is pretty close approximation to the experimental value of 217 nanometers.